In previous video, I talked about oscilloscope. Then many of you guys requested me to make a video on spectrum analyzer. So today in this video, we are going to talk about the spectrum analyzer. Spectrum analyzer is a complicated instrument to use. It is a crucial tool in many fields including telecommunication, audio engineering and radio frequency engineering. A spectrum analyzer allows engineers and technicians to see frequency components of a signal which can provide valuable information of a signal such as the source, integrity and the quality. So first let's see how to use this spectrum analyzer. The oscilloscope we are all familiar which displays the instantaneous voltage on the vertical axis against time on the horizontal axis. This shows waveform in the time domain, but the spectrum analyzer is different. It displays waveform in the frequency domain, displaying the amplitude in the vertical axis and frequency on the horizontal axis. It's like tuning a traditional radio receiver over a band of frequencies and making the points where the signal occurs. Except that the spectrum analyzer indicates the amplitude of all the signals with a high degree of accuracy. Spectrum analyzers are available in various forms. Some are contained in traditional cases which can be mounted in 19-inch racks, whilst others are more suitable for portable operations. Some may be incorporated into systems like PXI racks. Others are designed to be used directly with computers often connected via USB links, enabling the computer's processing power to be used. Each format has its own advantages and disadvantages, and a choice has to be made for its application. Despite the differences in the way they are presented, spectrum analyzers follow the same basic principles and the operations follow the same basic rules. Here we see a typical spectrum analyzer. Once it has been turned on, the most pronounced feature of what we see here is the display. Other features on the front panel include the soft keys around the display itself for some of the functions. But the most important control are contained in the keypad, which is used for the main functions including the entry of figures for frequency, span, widths and the like. One of the first items to be entered into the analyzer is the center frequency. The center frequency is used because the wanted signal can then be seen at the center of the display and other signals either side of it. Once the center frequency has been set, the span can then be entered. The span is the width of the frequency band that is displayed. As the span is reduced, so too the background noise level falls. And also, signal closer into the wanted one can be seen more easily. It will usually be necessary to adjust the level controls. The reference level can be changed so that more of the signal of interest is seen on the display. Some of audio analyzers had separate controls for RF and RF gain. These days, modern analyzers combine the two intelligently, so that it's just a matter of adjusting the reference level to place the signal with the peak towards the top of the display as shown. If you reduce the reference level too much, then the signal starts to disappear into the noise. So it is important to get into the right region. Typically, a minimum figure of 20 decibels between the signal and noise is required for good measurements. Much closer to the noise and the signal level will be seen to vary because the noise level is sufficient to add to the signal and affect the overall result. Here we see an amplitude modulated signal on the analyzer screen, but to see the side bands we need to adjust the span. As this is progressively reduced, the spectrum analyzer scans a smaller bandwidth and the side bands are seen. In reducing the span, the analyzer has two controllers linked together. The first and the most obvious is the span. The actual band that has been scanned, however, it also reduced the resolution bandwidth. This is the same as the reception bandwidth of a radio. The smaller the resolution bandwidth is, then the higher the resolution of the scan, the more detail there is. The downside to a narrow resolution bandwidth is that the scan takes longer to perform. As a result of spectrum analyzer links narrower resolution bandwidths to the smaller overall scan widths. Otherwise, they just take too long. The noise level also falls for lower resolution bandwidths because the noise is proportional to the bandwidth. This means it's easier to see lower level signals because they are not masked out by the noise. Taking the resolution bandwidth on its own backup, is possible to see that the detail is lost. For modern spectrum analyzers, our resolution bandwidth is normally automatically chosen to provide the optimum resolution for any given case. The very useful capability of modern analyzer is the ability to add markers that shows the parameters of a signal at a particular point on the screen. The most obvious one is a marker for the highest level signal. The marker shows the major parameter like frequency and amplitude. Normally it will automatically find the peak of the signal. Another popular marker is known as a delta marker is typically takes the second highest peak, giving the frequency and amplitude as well as the offset from the main marker, typically an amplitude and possibly frequency. This is very useful for determining the attenuation of spurious emission relative to the wanted signal. Some analyzers have a screen that show other marker capabilities. These will vary from one analyzer to the next, but this one show aspects like phase noise, decibels down on the carrier as well as host of other features. Spectrum analyzers rely heavily these days on processing technology. They often contain many inbuilt routines. These cover many functions, everything from channel power to harmonic distortion and third-order intercept to AM modulation measurements. Two routing that deserve special mention are phase noise and spectral emission mask. Phase noise is a critical parameter of many oscillating systems. High level of this noise can cause many issues. Unfortunately, all signals have some level of phase noise on them, as can be seen here. It can be difficult to measure phase noise accurately, but many analyzers these days normally have an inbuilt routine to do this. It notes the carrier frequency and then scans out from the signal using narrow resolution bandwidths, so that it can capture the closing phase noise. As scan moves further out, the resolution bandwidth will increase, but the routing will normalize for this. The standard for these measurements is to measure noise in 1 Hz bandwidth relative to the carrier, and measurements are expressed in the form so many dBcs per Hz at the given offset from the carrier. In this measurement, it can be seen that the result is minus 14.63 dBc per Hz at 10 kHz offset from the carrier. This screen shows a typical plot for phase noise. It can be seen to be reducing as the offset from the carrier increases. One important point to note is that on a spectrum analyzer, the phase noise is measured against the analyzer local oscillator. Any noise on the oscillator will be superimposed on the plot. Therefore, the oscillator should have a noise performance better than the signal being measured by the about 10 decibels. Other techniques like cross correlations are present in phase noise measuring systems, and this overcomes the issue, but these systems are normally very specialized and much more expensive. Spectral masks are very useful for seeing whether a signal and its spurious emission fall within acceptable limits. The mask sets out the maximum level at a given point. For this example, the signal in yellow can be seen and the mask can be just seen in red. As the signal falls within the red outline, it passes this test. More complicated example could be seen here with a wideband CDMA signal. In the test is ensuring that the level of spurious signals in adjacent channels falls below the accepted levels defined by the mask. Although analyzers' performance levels are very good these days, it is still possible for the input to become overloaded. When this occurs, spurious signals can be generated within the unit itself. This can be an issue because it may not be obvious whether these signals are generated by the item under test or within the analyzer. It is easy to check this. To see how this can be done, we are looking here at two tones with some additional intermodulation products that are lower in level. These could come from the unit under test or the analyzer. This can be checked by changing the input attenuation, and it can be seen in the case that the relative levels remain the same. This means that they are present at the input of the analyzer and not generated by the test equipment. So if you like to see more videos on electronic instruments, follow my channel and follow me on Facebook. See you in the next video.